thank Lucian for the introduction and remarks about the old days. And I want to maybe stand over here so I can use a projector. When I first came to the statistical laboratory in 1939, I cooperated on the problems, and I was supposed to be working there doing as kind of a research assistant, but I must say something of a novice since I had 1 year of statistics under Neyman and 1 year earlier before Neyman came, so my knowledge was not anything to boast about. But anyway, I first cooperated, I remember distinctly, on the problem of estimating the number of board feet of lumber of different quality in the national forest. And what distinguishes these problems from other ones which one often works on is that the scientist himself or herself worked with us. So the analysis was much more likely to be realistic, and we all learned a lot. And on the other hand, the analysis was much more likely to be quite more complicated and harder to do, and well, also to introduce interesting statistical problems. So everyone learned on it, and I think from that point of view, it was really very good. So there were many other problems in those days, I can't spell, and onward, and I list a few examples of ones which were published and which I could find and which I certainly remember very much about, and several in physics and genetics, soil sciences, in learning, in performance of students, earthquake damage, carcinogenesis, astronomy, which was of special interest to me, and so on. And each of these problems would come back later on, either with the same person or probably with someone whom he knew and came sent over to us. So they're just really, each one multiplied. So I first planned to speak on a sample of these topics, but it's entirely too much and would make each one of us entirely too skimpy in 1 hour. I tried next to take 3 topics on which there has been the most activity with continuing problems, and actually ones which I myself did quite a little bit on, so I could talk on them with some knowing somewhat better what I'm talking about. So one of them was on astronomy, namely the distribution of galaxies in space, and there's continuing interest in this topic. And then in carcinogenesis, which there certainly is continuing interest in changing all the time, but I'd like to say something about the stochastic process and how it might be altered. And then the third topic belongs to a category which we also, doesn't work, doesn't it? Weather modification, is it real? If so, how much and how far? And this has a category, has a distinction that it wasn't our idea that brought it, nor did any scientists bring it to us, but the state of California brought it to us, whether this new method would be helpful to California, which was short of rain very often, and this year, of course, in particular. And furthermore, it had some features which I found shocking, and I thought it didn't happen with scientists, but I'm not sure that how much it really happens. Namely, the data had to be very carefully examined. We found sometimes three successive analyses which had all been delivered, so they weren't hidden or anything like that, which were entirely different. And the first one showed that the cloud seeding was very harmful. Next one showed it didn't make any difference. And the third one, all on the same experiment, same data, showed that it was very helpful and was increasing rainfall by 15%. Well, it's kind of shocking to do this, and then you look and see how did they achieve this? Did they have a little trouble with their arithmetic? Well, the answer is yes, and all the mistakes were in their favor, but that wasn't enough to do it. They really monkeyed with the data, and I mean that word clearly. They lost some stations that were recording rainfall. They decided that some stations weren't working well. They recorded some stations on the wrong day. You just can't imagine how many ways there are that we found to could go wrong, and probably some other ways that they know about that I haven't found out about. So I think a lot of work is needed, and one needs to be warned that if somebody's going to make money over a certain method, care needs to be taken that his data is really carefully checked. Anyway, this is still going on. The problem hasn't gone away, in spite of the fact that in every single randomized experiment carried out anywhere in the world, cloud seeding has been harmful or ineffective, mostly harmful. So it's hard to believe that people would still be doing it. Well, the answer is because it's done when it's done operationally, not as an experiment and analyzed by the operator, it's helpful. So here's a reason to have randomized experiments. Well, what I want to do is start with galaxies, and I want to talk something about how Neyman and I and other persons, especially the astronomer C.D. Shane, and then other astronomers, Mayall, Abel, Zahn, and so forth, worked on an evolving series of problems. It started somewhat before this same year of the oath that was mentioned earlier, and a little before 1950, Shane came to my office to describe to me some problems that ideas that he had that, and wanted to know whether something could be done with them statistically. So I had taken courses from him in the astronomy department and knew him quite well, spent some summers at the Lick Observatory, got to know him better. Be that as it may, what happened is that when he became director of the Lick Observatory, going from Berkeley to Lick, the Lick Observatory had just started on a gigantic study of mapping, taking plates, big plates, 17 inches on a side, of graphic plates of the whole sky that's visible from the Lick Observatory. A tremendous number of plates that need to be done and a tremendous job in order to carry this out. And Shane, when he did it, didn't have any idea what he could possibly do with these plates, because the purpose for taking them was to wait for something like 50 years, when he would no longer be alive probably, and take a second series and see how much the galaxies and the stars had moved with respect to each other, to get an idea of the so-called proper motion of these objects, which are useful in several domains. Oh, he was working on this with one assistant, Wertman, and just took him to make a good plate would take a night, and it was just a tremendous job. He got the idea that he should use these plates in order to try to get an idea of the distribution of galaxies in space. And at that time, astronomers believed that the galaxies were distributed Poisson-wise, with a few exceptions of the very obvious clusters like Coma that everybody could see, and which were called lace on the petticoat by astronomers to indicate how attractive they were. So the problem then was, how could he make this analysis? And he had seen, and I had also, a paper published a year or two earlier by Chandrasekhar and Munch on studying star clusters, and the method that they had used, namely using the serial correlation between counts in successive small squares. So he had the idea that he could try to do the same thing and use that. If there is a cluster there, then there would be some correlation between the counts in successive squares. If there's nothing there, if they're not clustered, then if they really are Poisson, then the correlation should be zero. So that's what his idea that he worked on. So here's a picture. The idea is it has a tremendous number of galaxies on it, but as this synthetic plate is a reasonably good representation of the real situation, sometimes you can see here bunches of them, and they're bunched together, and sometimes you see there's more or less empty, like here, and the idea is to try to see if you can construct a model which makes sense astronomically and which will represent this situation. The model we took was a simple model And let me mention something in passing. Why is it that the astronomer who was testing whether this was Poisson distributed got the answer that a Poisson distribution would fit well? Because he didn't use a powerful test of the situation. And in particular, what he used was just to see whether the mean and the variance are the same. And I don't mean to say he's the only person that did that, because that's a very common test. But anyway, it didn't work in this particular situation. Okay, then. So what happened is that we made after talking to the astronomers, we made some simple assumptions, namely that every galaxy is in a cluster. But this, of course, is waffling out somewhat because clusters were allowed to have only one member. And then that these cluster centers, which need not be occupied, are Poisson distributed in the first model that we had. Later on, we had more complicated models, and that they were independently distributed. We showed actually that instead of you can have multiple occupation of each center, and you'd get the same. You would not be able to detect the difference from just using counts alone. So, taking these counts which Shane and Workman had made by sitting in front of a huge template with 17 by 17 inch plate and a magnifying glass looking at this, and it was a tremendous job. And I must say that well, maybe Shane too, I think he had his doubts, but certainly neither Naaman nor I believed that Shane would ever finish it. It just seemed a hopeless situation, and he did, and so I must say I can't help but compliment him on this tremendous endeavor. He not only did that, but he did something that other astronomers don't think of doing or don't want to do. He took some duplicate plates and made some duplicate counts so we could get an estimate of the error situation. There was already a slight estimate because these plates were 6 degrees by 6 degrees and they overlap by 1 degree, so there was a slight overlap on the plates, which you needed to do. Anyway, coming back to the problem at hand, next assumption was that there's some probability distribution of the number of galaxies in a cluster. This is not specified what it was. Then the next thing was that there's some probability distribution of the distribution of the distances of the galaxies from the cluster center, also not specified what it was, and independent from one to another. And the next thing was that there's some distribution of the brightness of galaxies. They obviously are not all the same brightness, and that this is the same for every galaxy. The distribution is the same for every cluster, and irrespective of the distance from the center. So putting these all together, we computed the probability generating function of the number of galaxies that you would expect to find in 2 squares drawn on here. The 10-minute by 10-minute squares was what they were actually using, so there are many, many, many of these squares on here. 2 squares, k apart, 1 apart, 2 apart, 3 apart, and so forth, and showed this. And we worked this out for some special cases, and more as time went on. And in particular, we worked it out for the case of a static universe first, and for an expanding universe later, and put these two together. And we got an excellent fit for this, and excellent. And we used the data and what was going on. We used in order to estimate the parameters, which you noticed was all, and estimate the functions, which are all not left there. We did this for special cases, which were suggested by the information available from special clusters, of which there are a few, and from star clusters, and worked this out. Anyway, what I'm trying to come back to say is that we were able to estimate using only what we call the quasi-correlation, but which I think would be more often called a factorial correlation, serial correlation between particular ones. As you probably know, when I have finite observations, the factorial correlation is more convenient to use than the correlation itself. And in fact, in this particular case, it's especially true because the correlation will depend upon the serial correlation, the Plains correlation, will depend upon the whether you use squares or rectangles or so forth, and astronomers did not realize that. They don't realize it today, and can make curious conclusions on account of this. So the quasi-correlation is no harder to compute, and gets rid of some of these problems. Anyway, using the quasi-correlations, we were able to obtain these estimates and work them out. First we did it for all the first we did it for all the 1 degree by 1 degree. Let's take the easiest problem first. And then we did it for all the 10 minute by 10 minute counts that Shane had made, and worked it out, and got a somewhat surprising result, that the estimates were not exactly the same for 10 minute by 10 minute and 1 degree by 1 degree, which indicate there's something wrong with our model. And it suggested to us, there are many possibilities that you could suggested to us that the fact is that the dense clusters are not built on exactly the same scale as the more empty clusters, and we tried this out, and actually you can make it fit very well doing that. You can make it fit very well doing other things too. Anyway, this is the sort of thing that we actually did. I brought with me today, partly because Margaret Stein was one of the authors, and partly because it's kind of entertaining that people would do such a thing by hand, which is what we actually did, namely this construction of this synthetic plate, which I already have up there. So what we did was to construct a synthetic plate that would, and the reason that we did it was to try to convince astronomers that what we were doing could actually produce clusters, and it would look like something that which they actually see in the sky, and they were very dubious about that. I think we have to realize what happens is what we had available and what was shown on our computations in the probability generating function was a very simple function depending on the 3 coordinates of the object in the sky, and depending on the really the brightness. But actually, when you come about it, we don't really have 3 coordinates that we observe, especially in those days. We observed just 2 coordinates, because everything is projected onto the photographic plate. A picture of the sky, everything is projected onto the sky, we say. So we have actually 2 coordinates, which are the projection, and then the trouble with the brightness, the intrinsic brightness, we can only see those objects which are sufficiently bright for us to see. So when this was done, we constructed a synthetic plate which would take this into account, and that's what I want to show on this particular thing here, because I think you may find it fun to take a look at. Now I really have them mixed up, so this one will come in later. Yeah, so this is construction of the, how did I get them so mixed up? Here we are. This paper is written by Scott, Shane, and Swanson, and we had the help of quite a few people in order to actually do this by hand. And Swanson is Margaret Swanson, who's now Margaret Stein, and I see her back there, so she'll probably remember this is a long, hard job. So what did we do? We took a published table of Poisson distribution. Actually, we used Kitagawa, I can remember that. And we read out of that the coordinates and plotted the coordinates of the computers of the plates cluster centers. You have to do much, much bigger. In order to make one plate, you have to go much farther than one plate, 6 degrees by 6 degrees. But as a cluster, which is very far away, can be mean enough to throw a galaxy onto your plate. You have to go farther out than you need to go. So we did that, and then we used normal tables, took the Maxwellian distribution of galaxies. We used a special case of the geometric distribution for the number per member, because most of them have a few, and it's only rarely that they have many, and this is very clear from what's going on. And so we we took the normal distribution for the galaxies, not for the brightness of the galaxies, and there's some argument about that, but anyway, this is what we actually did. And each time of these were trivariate normal without paying any attention, with that, independent of the direction. So that's what we're seeing here. We stacked them up, and that's what you can see what's happening here. I hope it shows. I think you can. Here's one up there, see it? Here's another one down here. Here's another one here. See how this one spills out? Here's another one here, and so forth. So these were just plotted by hand and stacked up by hand for each distance zone. Here, this one is 30 to 35. This one's 0 to 25, and so forth. And let's continue on. Here's a couple more. And you can see as they get farther away, 40 to 60 million parsecs away, then there's more and more clusters on top of each other, because we're actually, since we're going out in space, we get a bigger and bigger area, volume actually, which is under consideration. Okay. And then they were all put together. Let's take one of these where they're all put together. So here's a synthetic plate. And then the next thing we did, and I didn't bring everything with me, at least I hope not, we assigned a magnitude to each one of these galaxies and threw away those that are too faint, threw away those that fell off outside our plate, and it's very sad to throw away all that hard work, but it was all tossed out. So that's what we actually see what's left here, and here shows the result. Now if you take a look at this, you do not see, or certainly not very clearly, clusters of galaxies. Maybe you could see this one might be called a cluster, here might be called a cluster. But the interesting thing is that if I go back to to look at each one and see whether they really are coming from the same cluster, all have the same mother, same cluster center, the answer is no. Lots of them are piled up on top of each other. Also, if you look at some specialties, which you'll mention later, at that time, especially in Russia, it was very popular to find sickles, that is to say, kind of crescents. And so, yeah, you're right. So here's like this, or here's another one. They were quite relaxed in how much they had to, what they had to look like in order to be counted. And they found in almost all cases, those were not members of the same mother cluster. They came from other clusters which got stacked up on top of each other. There are exceptions, of course, but certainly only one or two of those would come. So I want to mention that because it will come later. So now we have actually made it a little more realistic, namely the varying limiting magnitude, namely that when you take a photograph, even with an astrographic camera, the limiting magnitude is not the same in all parts of the plate, and a lot of work was done stacking these up to determine the shape of this, and I won't go into details about that. But here's the actual one that we finally came out with. I want to call your attention to something like this, which we'll come to later. Get even bigger shapes. This on the modern days would be called a bubble. Here's the actual plate with the stars taken off, only the galaxies. And I would say, if anything, there's more clustering on the actual plate, because particularly it happens to have a piling up in that upper left corner. And this plate was just one out of some 3,000 plates which were taken. The size of the symbol, the bigger symbols, are roughly brighter than the others on an arbitrary scale. This is one, and then it was made a second time. It recharted without referring to the other plate. and so you can see something about the errors, which I won't take the time to say anything about, but you can see what's happening here. Here's a comparison using counts. So here for two different plate centers, here's 16 actual plates in the synthetic plate, something of the range of the 16 actual plates and how they compare with the synthetic plate, and the relative frequency of finding 0, galaxies 1, 2, 3, 4, etc. going up. And similarly here for the comparison of two actual plates, again just selected at random. I could take more of these if we wanted. Actually, we have that in the paper, and you see that the difference here, if anything, is not any more and perhaps is less than the difference between two actual plates, which are selected at random, not specially picked down. Okay. Now we then, how many more minutes do I have, Lucian? Oh, that's okay. Oh my. Okay, then I'm okay. I hope, at least. Then what I wanted to say is that we went on for this to many other problems which are of interest in the distribution of galaxies on space. In particular, we under the assumption that galaxies are in clusters and are, according to our model, or some more complicated models than this, for example, superclustering and the addition to clustering and other things of this sort, we worked out to test what the distribution might be, what the real distribution might be, in particular, for example, whether the universe was static or whether the universe was expanding. Just at that time, though, came the suggestion that it's not that everything started with the Big Bang, but that there was continuous creation of galaxies, as Gold, Hoyle, and Bondi. And if that's the case, then our model isn't working because we just had everything starting at the beginning. In our case, we could compute what, if you assume the simple case was no creation, or some simple models of creation, then we could estimate what the expansion of the universe should be and work it out that way. But if you have this hole in it, then it's not such an interesting situation. At that time, we then had used the data of Shane to answer also other questions about the interlocking of clusters, because one would be suspicious in the slide that I showed earlier that there's lots of interlocking of clusters, that they're running into each other, and this makes a difference in the evolution, because if they actually are colliding, then the evolution will be somewhat different than if collisions are very, very improbable. Anyway, the next problem was to try to see if we couldn't extend these results and use the new data that would become available in addition to what Shane had just obtained, but after that, in order to try to, say from the southern hemisphere and from bigger telescopes, in order to try to test the model better and to see what's actually happening. And this would not become available for quite a time, and before that we found ourselves going to the Lick Observatory at least once every 2 weeks, sometimes more, and it was really very nice there, partly because they were building a big 120-inch telescope, but it wasn't built yet, and the telescope wasn't there yet. So there was this whole big building, all quiet and all empty, and we worked in the library, which itself was almost empty. Just had a few old books which thought the Franco-German War, Prussian War was still going on, and the French are about to win it, and various other things like that. So the problem was, it was a really very, very pleasant place to work, and we would come, and after a while Shane would come and say, stop that arguing and listen to what we're going, another idea that I have, and so we would do that. We were allowed to use a refrigerator, which actually, of course, was made to keep the plates cold, but it could keep a little cream cold too, so it worked okay. Then, we also met, of course, many astronomers, because many astronomers visited the Lick Observatory, so we learned about many interesting problems. But everything comes to an end, and when there wasn't any more data, and also the Lick Observatory headquarters moved from Lick to Santa Cruz campus, and Mayo, for example, got another position as director of the new Kitt Peak Observatory, and so forth. Life became more complicated, and we started working on other problems such as carcinogenesis. But I want to put that off for just a minute and say what's happening now, because now there's a tremendous amount more data than there used to be. There used to be just the positions and very, very few velocities, which allowed you to estimate the distance of the third dimension. Very, very few. I remember taking these, helping Mayo take these. It would take him sometimes one whole night, 2 nights, even 3 nights in order to take one of these plates. That's a long time to stay up all night in the cold. And he would organize bridge games, and the dummy had to be the guy, the telescope, and the rest of the people couldn't. So anyway, we came back again to this problem only much more recently with the new data that's now available, especially the data that's available from some of the people who are now on the staff in the astronomy department, in particular Mark Davis, because they invented a new way to measure, well, first place, much more elaborate counters. Plates were observed, and particular photon counters were invented, and we get much better magnitudes, much better positions, and much better radial velocities over a whole area. And also astronomers learned not to just observe their favorite galaxies and their favorite clusters, but to take complete samples or random samples, so forth. So we got data which are more convenient for us to work on. Anyway, the next thing that was done then was, and also observations were made in different wavelengths, made a tremendous difference in the results and allowed us to get a more flexibility in what was going on. So let me say something about that, and to notice that what happened when you started taking, now I have brought this picture. Shane and Werton made I'm all twisted up, made a photograph of their planets, but they has the stars on it, and it's hard to use by eye because the Milky Way, is so predominant in that particular situation. So I brought this. Oh, thank you. So I brought this with me, which was made by Peebles from the counts of Shane and Werton, and what they did was to make the more count. These are not observations at all, but they're the cells on which Shane counts. You can see how many there are because they're all blurred together. And the whiter it is, the more galaxies Shane and Werton counted. So you can see it shows how the density changes as you move across here. And if I take a look at this, I don't see any particular great patterns or great excitement. I don't see any. It depends how, on your point of view, I guess, what you actually see. You certainly see clustering, very striking, and so there must be, that's very striking. You see some patterns like this. I don't know. Here's another pattern like this that one can see if you take a look at this. But what became stylish in physics was not to talk about points of so forth, but have light or energy distributed in planes. So we'd have these complicated situations about that. What we're really observing was not the situation went stepwise. First, everybody said, okay, everything's in clusters, which was already a big change from 1950. Then they said the next thing is, well, we shouldn't be paying attention to the clusters, we should be paying attention to the voids. At first that sounds like semantics, because you have clusters, you must have voids. But anyway, onward. Then the next thing was to look at how these voids were distributed. Are they actually in some kind of two-dimensional situation, how the energy is distributed? Then came the next thing where they would be actually in bubbles with something empty in between. And something wrong? Okay. Let's stick this. And so now I'm going to say something about that. So here's the entire, using a different catalog made by Zwicky and another one made by Nilsson put together, so it doesn't go so far out as Shane, which goes out to beyond 18.3. The brightness is measured, goes on a backward scale, and the part that's visible from Zwicky, where Zwicky was observing, which was in Pasadena, was the part that goes, you can see where those heavy ticks are. This part is quite complete. This part right here is quite incomplete because not all of this is observable, so you really should ignore this part down here and see if one could correct from this, but it's hard to do. Now, with the new information that's available, so not only these two coordinates on the sky, but in addition to that, I can take the coordinates on the sky and take a fixed coordinate in one direction, say here the right ascension is changing and declination is held fixed at 29.5 up there, so not too far in the lower strip that's going across, and cut this at according to the radial velocities, which is a measure of the indicator of the distance. So up to 5,000 velocity, kilometers per second, 10,000 and 15,000. So all that are less than 15,000 are shown here. So I take a cut across the three-dimensional situation. Now look at this. Anybody would tell you, certainly an astronomer would tell you, that those are not Poisson-wise distributed. Something else is going on there. I see a pattern there which is very striking, these empty places and so forth. And this actually is taken, the place that's chosen here is right where I cut across the coma cluster, which is probably the densest part at this particular radial velocity. So I have plenty to look at and I get this kind of pattern here. And so let's see what happens in one down. Here we are again, centered at a slightly different place, and at a different place yet. And so you can see that the thing does extend from one cut to another cut. I think one of these is two put together. Yeah, this one is two put together. And here I have a different magnitude limit so that I only get the brighter galaxies, but this part keeps the same and that part keeps the same. Now the problem that comes here, as you very well realize, if you allow me to select how I make the cut, then I can find things which I would not be able to find. If anything is there, and if I'm clever enough and I work hard enough, I can find something that that attracts your attention. And this is a real problem with this sort of situation, that how much of this is real and how much of that is because they found things which happen to line up. And that's why I want to show you the last one also. Also, what's happening as you go out, if I have other places I'm not able to find this, and it was suggested, I've forgotten the name of the person who did it, Postman, suggested by Postman, that this is because there's a sampling problem which is going on here, namely that here if I have a 75%, get it right, 50% sample of what's before, then this is what I happen to see. Here I have a 25% sample, here I have a 10% sample. The details which were shown before, the outlines of the bubble, tend to disappear, tend to wash out. The same thing happens with other things which happen with galaxies. We actually published a paper about the problems that one has and how one has to correct due to the fact that you can only find a cluster if it has, well in our case where it was easier, it has to have enough members and they have to be bright enough. Here you can only find a ring if it has enough members and they're bright enough to show. Same problem that's just going in there. The question then that is facing us at the present time is, how can I test which of these is correct and which of these is not correct? I think I've used them up. No, here's one more. But it just, here we change the position and the picture changes, and that's the same sort of thing I was saying. Picture will look different according to where I select, and if I get in 3 dimensions and take cuts across, 2-dimensional cuts across 3 dimensions, I have quite a little flexibility in what I can take. And if we'd had a Macintosh when this was made, they probably could have done better yet. Anyway, that's the problem that we're actually having at this particular time. So there have been some cases found where this is very striking bubble situation, but it's unusual, and the suggestion is it's unusual because we only find it in Como or Boise or other places where the density of galaxies of clusters and galaxies is high, so they have more chance to find it. Okay. So what we're trying to do, or I have been trying to do for several years, is to, and I'm not the only person who's trying to do it, is to try to find a method of distinguishing between, say, bubbles and clusters, or, there's even another one. You can have fun if you want. So if I take this and go back and paste some different layers together, then I can imagine that this looks like a cheese, or looks like a sponge, or some other word like that, and you can select then, try to test whether that actually is going on or not by putting the whole thing back together and making this test. And this is not empty, because one uses this in particular for certain theories in physics, which are just theories, to see what's actually happening there, and then actually using the galaxies as a laboratory. One also tries to use this to put together to see how the universe has actually grown during the short time at the beginning. If we start with the Big Bang, how do we get these irregularities in the distribution? And it's quite sensitive, of course, to what you put for bubbles or whatever this actual situation is. So it's of interest to try to find out. Anyway, those problems are still with us, and actually there's many more complications which could be mentioned. For example, the favorite one of Mark Davis, who's a leading person on this sort of situation on our campus, is with cold dark matter. And I can't see the cold dark matter, but it is interfering with the actual situation and adding to the complications of what you actually observe. Now the next thing that we talked about, and things that we spent a great deal of time on, and many persons in the statistics department have worked on this, are the problems having to do with cancer, especially with carcinogenesis and the growth of cancer, or how one might be able to change the growth of cancer. And I might say again that we worked on this, as I mentioned already, with the astronomy problems. So we went to Lick Observatory almost every weekend, certainly every 2 weeks. And in the case of the astronomy, of the carcinogenesis, similar things happen. On this campus, there's many people working in carcinogenesis whom you can talk to. But also, for example, what Naaman did at when he first started working on it seriously was to go and spend something like a quarter at National Institutes of Health in a special building, actually, which turned out to be the original residence of the people who gave the land for NIH, and to talk with other people right there on the place so you could see what's happening, gave a series of lectures and so forth. I just think that, and those are the cases where we found the most interesting papers, most interesting results, because I think the reason probably is that we had a better understanding, better appreciation of what people are actually doing, what the scientists are actually doing. Anyway, the problems that we worked on there were especially concerned with, let me turn this off. are especially concerned with trying to see what the mechanism is, and actually you said the same thing was happening in astronomy. What is the mechanism? Even though we have a simplistic idea of what the mechanism, what is it? And can you represent it by a single process, which is what was started to thought at the beginning, or is it a multiple process? Does the cell make several changes, or does the cell receive several insults in order to become, or do they interact somehow? What is the actual situation? The favorite one for us to work on at that particular time was to compare the single hit, which does not fit the data. There's several experiments where it doesn't fit, and even though some of them are a little hard to explain to biologists. And the second thing was to see what might fit. Can I have, there's two changes. Suppose I have the cell receives some injury and then undergoes a semi-permanent change. Does this change immediately make it turn into a cancer cell? For example, does it change the birth rate and death rate so it makes it turn into a cancer cell? Or is it the daughters of this where this takes place? And that's the sort of situation which we were actually studying and which we were actually working on to see what happens. Now the problems are now more complicated. We're working on the cases not only does the cell itself receive damage, but the surrounding area usually receives damage. Surrounding area usually has some kind of mechanisms which are activated by this damage and try to repair the damage. And if the damage is repaired properly, it may well recover perfectly all right. If the damage is repaired bad enough, it may die and then the cancer doesn't resolve. But if it's repaired badly, then it may result in a cancer. So the problem is much more complicated than it used to be, but I think at the same time much more interesting. And we now have a student who also is considering the case that suppose that we change the immune process, which is part of the process which is helping with the damage situation, if we improve the immune process, how does it work that it improves the actual situation for cancer? How does it work if we destroy or damage the immune process? How does it work? So forth. So these problems are still going on. I wanted to spend, have I got another 5 minutes? Thanks. But I want to spend just a couple of minutes returning to the cloud seeding problem, because it's an interesting problem, and it gives me an example of which I hear over and over again, and which maybe I didn't think about in astronomy, because I had learned astronomy for a long time, so I kind of felt I knew things. Of course, I didn't really know things. They were just familiar to me. Whereas when I started working on meteorology, I started thinking, I came and I just really knew nothing about meteorology, or essentially nothing, and tried to see what was happening. And I was shocked to learn that most of the people who were working in meteorology had very little knowledge of what's going on, in particular the people who were in the cloud seeding. And it came to a curious phenomenon which came out of World War II, in a meeting which was made about how many meteorologists you'd need in order to help with the bombing and so forth. A mistake was made, and it was recorded. The number that was recorded was off by something like a factor of 10, according to most stories. Exactly what it was off about, I don't know. But certainly, many more meteorologists were trained at that time than were needed, and some of them are sitting in this audience. So, and the trouble was, obviously, they're not well trained, because it was very short training and for a very specific purpose. But that doesn't, they had trouble getting a job probably, and they turned to cloud seeding, and that's one of the real troubles that we have with cloud seeding. And so, you laugh, but it's not funny. So the situation then came to our attention, and we had to learn at least as much meteorology as they knew, and probably more, so that they wouldn't spend their time telling us that it was all our ignorance that we misinterpreted their results. Anyway, the problem came up, and the problem is much more complicated. And we see here the influence of statistics, and in particular in model building. First we had one-dimensional models of how rain falls, and two-dimensional models, and now three-dimensional models, and even more, much more sophisticated, also much better observations from outside, which help us. But curiously, the observations that you get from radar do not help you too much for predict rainfall, and certainly not to predict hail, because it so happens that they can't distinguish between ice and water at the wavelengths that they're using. So you get very complicated sort of situations in those particular cases. And the similar thing starts happening with the observations which come from the satellite. They don't give you everything you want to have. And we could say something why this is, but it's not. There's a big difference between rain on the ground, hail on the ground, insurance damage due to hail, and radar measurements in different frequencies, and satellite observations in different wavelengths. So you cannot kind of paste it all together in a simple way at the present time, although you can later. We ought to be able to later, I should say. Anyway, coming back to the problem we had at hand, it is clear that the method that we had of how to affect the, say, hail, or how to affect the rainfall has something wrong, in a sense that it just didn't work. And it didn't work with such a bang. You didn't have to be a statistician to see that it wasn't working. It just was doing more harm than good. And it's lucky that we managed to persuade them in doing the experiments to do randomized experiment. Usually we can only persuade them to do completely randomized experiment, but even that is a big step, or sometimes, anyway, even that was a step forward. So we were allowed to, we could make the comparisons between the two and be able to make some statements about what was being helpful or what was not being helpful. But then we discovered a very amazing thing. And we first found it in a big experiment which was carried out by the University of Chicago, at the meteorologists at the University of Chicago in Missouri, so-called white top experiment, and that's just a code word that they had for it. We found that not only did it decrease the rainfall downwind from where their target was, but it increased it for 10 miles away, for 20 miles away, for 60 miles away, for 120 miles away, and probably even farther, but we didn't have enough data to observe this situation so far away. So there's something funny there that we didn't understand what was happening, and somehow it seemed to us at least very unbelievable, and even more unbelievable to the meteorologists. Then we found that the same thing that was happening, had to find another place where the cloud seeding was going on, and there were observations being made far away. And there was such a situation in Arizona, and more or less the same years they're going on, experiment which was made near Tucson, in which we could make observations in a very compact and large set of rain gauges, which were put up by the Forest Service, not for measuring rain or anything like that especially, but for studying the distribution of rainfall in that area. As you know, when it rains there, it rains like everything. It doesn't rain, so you get flooding damage and damage to the soil when there's rain, and they wanted to study this and see what could be done about this and what could be planted or something rather to alleviate these difficulties. Anyway, we used these observations and managed then to find that again, that there was a very large downwind effect, and it was very big far away from where the target was. So even though this very mountainous region which is occurring there, the problem was very big difficulty. So I think there's another difficulty that we have to worry about, is that if you do cloud seeding in your backyard, you may be affecting areas which are far away, and if it's harmful in your yard, it may be even more harmful farther away. The problem requires much better theoretical knowledge of what is going on in order to do this. Similar thing happened also in Switzerland. The observations, we obtained data from Mussolini's old palace in Rome to get the Italian data there, because it's owned by the Air Force, and get the data and look and see what's happening. And we found that again the rain in southern Switzerland is coming from the Mediterranean. It goes up over the Alps and occasionally rains in Switzerland itself. We then were able, because actually weather observations were very good in Switzerland, to get observations in any particular place that you wanted, and they were selected not by us but by the Swiss meteorologists, and found that there was a big effect of cloud seeding far, far away on the other side of the Alps, very hard to believe. And it was the sad part here was again that it worked in a negative effect, namely that they were trying to stop hail, which has damaged their crops, especially their tobacco, and instead they were increasing the amount of hail, not only locally but also far away. So the problems go on. Thank you.